In this video, our fourth in our series on sequences, we want to look at the recursive definition of a sequence. This is another way we can write a sequence in a different kind of form. Now, some sequences are easier in this way, some are harder, but it's just a different way for different types than we've already looked at with arithmetic and geometric. First, let's talk about what it means to be explicit in terms of a sequence. First, let's talk about what it means to be explicit, what the word means. Now, usually when you hear explicit, you're going to think bad language, swearing, curse, that kind of stuff. That's not what explicit means. Here's the definition of explicit. The definition of explicit is something that is clearly expressed or demonstrated, something that is straightforward. That's explicit. So when you think of like lyrics and songs, you know, an explicit lyric means it comes right out and talks about drug use, let's say. There can be songs, you know, where there's drug use that's implied. It doesn't come right out and say it, but there's a hidden meaning that you know there. Explicit means there's no hidden meanings that come right out and say it. So in terms of music, what that means is explicit lyrics means there's vulgarity, there's sex, there's drugs clearly in the lyrics. Not, let's say, a song, you know, like Puff the Magic Dragon, which maybe it talks about marijuana, but it's not explicit. It doesn't say it clearly. So how does this work for sequences? An explicit definition of a sequence is a sequence definition, a formula that's based on n. So as we looked in the last couple sections, if we had t sub n equal 2n squared plus 7, that's an explicit definition. If I want to find the first term, I can put 1 in for n, get 9. To find the second term, I can put 2n for n, get 15, and then 3n, and then 4, and so forth. And that one's wrong. Let's go back and change that. I didn't do my arithmetic very good. 3 squared is 9, 18, this is 25. 4 squared is 16, times 2 is 32, is 39. Now, the advantage of an explicit formula is this. If I want to find the 50th term, I can just substitute in 50 and figure out what that is. And if I did that, 50 squared is 2,500 times 2 plus 7, I get 5,007. So that's the advantage of an explicit formula. You can just plug it in and get any term you want. We want to look at today what happens when you use a formula that doesn't work that way. Consider these sequences. 1, 1, 2, 3, 5, 8, 13, 24. If you're trying to 21, excuse me. If you're trying to figure out what the next term is, the next term would be 34. The next term would be 55. So if you've never seen this before, this is called Fibonacci sequence. And the pattern is I add these two terms together to get the third. So I add 1 and 2 together to get 3. I add 2 and 3 together to get 5. 5 and 8 is 13. 8 and 13 is 21. 21 and 34 is 55, and that continues on. Now, what's hard about this is your next term is based on your last term. So how do I come up with a formula to know the 100th term? Well, this is not arithmetic. It's not geometric. I can't use those formulas. So now what? Here's another one. 2, 5, 9, 14, and 20. I add 3. I add 4. I add 5. I add 6. Okay, my next term is going to add 7. That's 27. But if I wanted to find my 20th term, how do I do that? If I have an explicit formula, I just plug it in. But if I don't, I need to find every single term. So here I'd have to find, if I wanted to find the 20th term, I'd have to find the first 19. Now the way we can kind of write these formulas out is something called a recursive definition. Now a recursive definition always has two parts. It always has a starting point. This tells you where to start. And then it has some formula, some equation to help you calculate it. Now think about this in terms of directions. If I was going to give you directions to my house, and I say at the stop sign, you want to take a right, and then at the next stop sign you take a left. And then the house is the second one on the right. That's great, but I haven't told you where to start. So those directions are pointless if I don't tell you where to start. Likewise, if I just give you the starting point and says, well, start in the parking lot of the school, and then go there. That doesn't help you either. So you really need both of these. And the one people always forget is the starting point. This is a key. Don't forget the starting point. So let's look at an example. Our starting point is t sub 1. That's our first term. And our t sub n formula is t sub n, some term, is equal to t sub n minus 1 plus 2. Now, this form right here, this is just a notation that means the last term. So if I have t sub 2, 2 minus 1, this just becomes t sub 1 plus 2. If I'm t sub 3, the last term is t sub 2 plus 2. If I'm t sub 4, the last term is t sub 3 plus 2. So this is just a shorthand notation, which means whatever your last term is. So now t sub 1 is 3, 3 plus 2, so my second term is 5. And to find the third term, I need that second term. So that's 5 plus 2, which is just 7. And to find my fourth term, I need that third term, which was 7 plus 2 is 9. So a recursive formula is always based on that last term. I can't just jump ahead to the 50th. Because to get the 50th term, I need to know the 49th. I can't jump ahead with the recursive formula. Let's look at another one. My starting point is 2. And my formula is 3 times t sub n minus 1. That means my last term. This is just the last term. Minus 1. So it's 3 times, I'm on the second term. My last term is the first term, minus 1. That's going to be 3 times 2 minus 1. So my second term is 5. My third term is 3 times the last term, which is t sub 2. And t sub 2 was 5, so this is 3 times 5 minus 1, which is 14. And my fourth term is 3 times t sub 3 minus 1, which is 3 times 14, that's my third term, minus 1. And 3 times 14 is 42, minus 1 is 41. So there is how we can find a first few terms of an arithmetic, or excuse me, a recursive formula for a sequence. Now here, since we just used just the last term, I need the starting point of t sub 1 is 2. But let's say I have a formula that has t sub 1, which is my last term, and t sub n minus 2, which is the last 2 terms. So now I need the first 2 terms to kind of get us started. So my third term is 2 times the last term, well, if I'm at 3, the last term is t sub 2, plus 2 terms ago, which if I'm on 3 minus 2 is 1, this is T sub 1. And that would be 2 times my second term, which is 3, plus 1, which is 7. My fourth term would be 2 times T sub 3 plus T sub 2. Notice I'm using the last two terms. So this is 2 times T sub 3, which was 7, plus my second term, which was 3. That's 17. And my fifth term is 2 times T sub 4 plus T sub 3, which is 2 times 17 plus 7. 2 times 17 is 34, plus 7 is 41. And notice, most of these sequences have not been arithmetic and they've not been geometric. So we really can't write them with our other formulas that we have used to this point. This is the only way to write them, recursively. So let's say we have this sequence, 3, 7, 11, 15. We want to write a cursive. So a recursive formula, you always need two things. A starting point, and then the formula for the next term. The starting point is easy. T sub 1 is 3. Everybody should get that part. Now the formula. How do you get the next term? What you want to do is try to figure out what is the next term. What's the pattern? And in this case, add 4, add 4, add 4, add 4 is 19. So I add 4. So it's my last term plus 4. There is my recursive formula for this sequence. Now I know what you're thinking. Hey, but wait a second. Isn't that arithmetic? Couldn't I just write T sub n is 3 plus 4 times n minus 1 like we did previously? And absolutely you can. That is an explicit definition when all I have to do is plug in the n. If I write a recursive definition, I need the two parts, the starting part and the formula based on the last term. There's two different ways of writing the same sequence. So be careful and see when is it asking for a recursive definition and when is it asking for an explicit definition. Now we looked at the one sequence earlier which was Fibonacci's. And Fibonacci's is 1, 1, 2, 3, a very, very famous sequence in math. And the recursive definition is you add the last two. So we have our first two terms, and then our next term is just the last term plus two terms ago. A very simple definition. But this can also be written as an explicit definition. This is not simple. This is one I got off of Wikipedia, and honestly, I don't know how you figure it out. Somebody much smarter than me was able to figure out, here is the explicit definition for the Fibonacci sequence. And I don't know how anybody ever would figure that out with the square root of 5s. Way too complicated for me. So sometimes it's very easy to find a recursive definition. This one's fairly easy. Really hard for explicit. If we go to our last example, it was almost probably easier to find explicit, but both were pretty easy. Here is one with some Fibonacci's that's very hard. All right, you're ready for our homework for sequences number 4.